Welcome to Elementary Algebra. The book is by Harold Jacobs. I'm your presenter, Molly Crocker. This material is copyrighted. Chapter 1, Lesson 9, The Distributive Rule. But first, a little review. I want to do a review of operations, but I also want to show you some calculator tools. A problem such as this could involve a lot of arithmetic. If you're a math nerd, that would be fun. If arithmetic isn't your joy, then let's pick up your calculator. First, type that expression in so it looks like the one at the top. The TI-83 version is going to look a bit different, as in the screen on the right. Now, I want to bring that original expression, the one on the top line, into a line where I can edit it. Look below the calculator screenshot and you'll see key press history. Pressing the second button and then the enter button repeats the entire expression without retyping it. This is why you don't want to be in the habit of pressing clear after every entry. Anyway, you'll see your cursor at the end, and now you can navigate somewhere in the expression to add parentheses and see what happens. I'm going to go to the beginning of the expression, and my cursor is on top of the first one. I want a start parenthesis to appear here. You'll use the left arrow on your navigation pad to make this happen. Pause the video until your screen looks like this one, with the cursor at the beginning. Now, notice the key press history and follow it until you get what's on the screen. That del button that's near the navigation pad sounds like delete, which it is, but pressing the second button first gets us the insert button. Do you see the tiny ins, INS, above the del button? That's insert. A start parenthesis was inserted at the very beginning of the line. The button sequence second del will insert a space where you can type what you want to the left of the cursor. So second del start parenthesis puts a start parenthesis before the first one. The next keystroke in the key press history was right navigation, 6 spaces. Follow out the rest of the keystrokes. You actually don't have to navigate to the end of the line after you insert the end parenthesis. You can just press enter and you'll see the result. Isn't that handy? Next, let's get that original expression back so we can edit it again for the next problem. Do you remember the sequence? Press the second button, then the enter button. But to get the entry that's on top in the very first line, do this sequence twice. This is what your screen should look like, and the key press history that got it there. If the line you want is 3 lines up, then you'll use the second enter sequence 3 times. Well, now, you can use your calculator to play with the parentheses to get what you want. How about something as large as possible? Remember, the delete button removes what's under the cursor. The second delete button sequence puts your cursor in an empty space to the left so you can insert some characters. You're allowed to insert characters until you navigate away or press enter. In other words, the insert is on until you go somewhere else or press enter. If you need to start over, then pressing clear once will remove the line you were working on. Pressing clear multiple times will remove all of the history. Don't get into the habit of doing that. Do it only when you need to. Now, play with this expression. Add 1 set of parentheses to get the largest possible result. Pause the video here. Here's how to get the largest possible number with just one set of parentheses. Try this one. I'm not going to offer a solution. I want you to play with it. You can use parentheses. I'm not going to show an answer. On to the lesson at hand. In 1940, a severe earthquake struck the Imperial Valley region of California. It took place along a fault that runs through the orange grove pictured here. The land shifted along the fault, carrying the trees on each side of it in opposite directions and breaking the regular pattern of rows in which the trees had been planted. Does the shifting of the columns suggest another way to count the trees? Now, this is a little problem, but it will suggest something you might be able to do with a much larger problem. The shifting has divided a single group into two smaller groups, one with 3 columns and one with 6 columns. This example is for a pretty small number of trees, but it suggests how to break up much larger groups into smaller groups whose sizes are easier to handle. It might be in tens or it might be in hundreds. In our example, there are 6 trees in each column. The first group has 3 columns. The second group has 6 columns. Do you see the 3 plus 6 grouped in parentheses? Now, we'll break up that group and distribute the 6 in front to each part of the group, so then there are 6 3s and 6 6s. 6 3s is 18. 6 6s is 36, which adds to make 54. So those are the same. 6 times 3 plus 6 is the same as 6 plus 9. Or 6 times 9. You knew that. 6 times 9 is 54. I told you this is a little example. The distributive rule tells us what to do when multiplication is mixed up with addition or subtraction. We can handle it like this. Here the rule is expressed in variables. In the first example, the a is multiplied to a sum. In the second example, the a is multiplied to a difference. In each example, the a is distributed to the terms of the group. Remember, terms are expressions that are added or subtracted. Let's back up a bit. You've actually been using the distributive rule since you were doing multiplication with double-digit numbers. The distributive rule tells us what to do when addition or subtraction is mixed up with multiplication or division. 8 times 71, in that problem, we'd typically stack up the smaller number on the bottom. Then we would start from the right and multiply the 8 by the 1, and then the 8 by the 7. But remember, that's not really a 7, it's a 70. That's what gets lost in this algorithm where we stack up the numbers. Do you agree that the stacked up example and the horizontal version will have the same result? Sadly, the version on the left is one of those algorithms for arithmetic that tend to amputate skills for algebra. What's an algorithm? It's just a set of rules to follow so you get a result. Instead, lay it out horizontally and think of it like this. When we had it stacked vertically, we multiplied the 8 by the 1 and then the 8 by the 70. But if we work from large to small, distributing the 8 to the terms of the group, then we can do this problem in our head. 8 70s and 8 1s, and means add. Here's what we ought to have taught you in arithmetic. you would have been freed from paper and pencil, and the distributive rule for algebra would have been no big deal. Here's an example with a variable. You can think of it this way. There's a group, that's the parentheses, and the group has an unknown that we're showing as an x and 6 pennies if you want. There are 4 such groups. So how many x's are there? There are 4 x's. And 4 groups of 6 pennies would be 24 pennies. Say that out loud to yourself. A group of x and 6 and 4 such groups is 4 x's and 4 6's, or 4x and 24. A group of x and 6 and 4 such groups is 4 x's and 4 6's, or 4x and 24. That's how you might be able to read each one of those lines. Now, it doesn't matter if we do it forwards or backwards, because the order in which things are multiplied doesn't matter. The group times a single-digit number is the same as a single-digit number times the group. Here's an example with the difference. Note that the sign in between the members of the group stays the same after the distribution. How could you say this one in English? 4 multiplied to the group x minus 3 means 4 x's minus 4 3's. Simplify the 4 3's to just 12, and the result is 4x minus 12. Again, it doesn't matter whether the 4 is in front of the group or after the group. Let's look at that rule again, as we would state it with some letters. This is how mathematicians generalize this rule. The distributive rule tells us what to do when multiplication is mixed up with addition or subtraction. Multi-digit multiplication also uses the distributive rule. Study this for a moment. In the column version on the left, every digit in the second number is multiplied to every digit in the first number. In the algorithm, we keep track of place value by moving left 1 and adding zeros to hold that place value. Some of you have been taught to put zeros there. Then, every piece in the first group is multiplied to every piece in the second group, just like you would do it if you were laid it out vertically. With a little practice, if we worked from large to small and added the products together from large to small, we would be able to do double-digit multiplication in our heads. Freedom from paper and pencil. Read carefully the examples in your text and then proceed to your homework. That's all for now.